Yeah, howdy. How's it going today? Yeah, so I'm just here to talk a bit about what we're doing at Rolls-Royce PLC within quantum computing, particularly for power systems, because that is what we care about. We care about the power systems both of today and the future. So just like a little overview of the things we're going to be talking about today. So we view quantum computing right now as being a really exciting time. I mean, we're seeing all these really cool hardware devices and algorithms, but they also they do struggle. They struggle with a variety of different issues, whether it's barren plateau phenomena or just like errors that propagate through circuits. And so we also have a focus just kind of on the future, towards when we have fault-tolerant devices and we can run way cooler algorithms in the future. But a bit of some context, so pretty akin to what everyone else has been showing. So we have 5 different big business areas at Rolls-Royce. So the one that we're probably most familiar with is the civil branch, and so this is the actual jet engines that are on many of the planes that might have gotten some of you here today, or maybe not. And then along these, I like to also highlight the electrical and the small modular reactor, because these are really going towards lower emissions and just our future plan of getting towards a cleaner Earth. Yeah, and so along the electrical, I also like to point out our Spirit of Innovation demonstrator plane that we put out last year. This is kind of like an example of an all-electric vehicle that is kind of guiding where we want to be going in the future towards electric engines. So it's pretty cool. It's got some records for the fastest all-electric vehicle. So yeah, the main thing that or one of the main tools that we really use when we are trying to make more efficient and better engines is computational fluid dynamics. And so this is a paradigm of just really modeling these really intense systems and really trying to get down to the almost to the microscopic level of modeling. So today we're able to model our engines at a pretty fine area. And so on the right here I have a visualization of a turbine compressor. So this is like the part of the engine that gets the most, that really compresses the air down the most. And so we're modeling this with 4.6 billion cells. So it's like little units around the 360 degrees there. And this is being modeled on one of our supercomputers in the north of the UK. And so in the future, we have a goal of getting to 1 trillion cells by 2025. And so this is pretty cool. It will let us, we advance the precision with which we can model these. We're able to just get more efficient engines. And so that is kind of the goal. But usually we start from these simple verification test cases. So like this one on the left. So it's a very simple test case of just like kind of a square, and we're just looking at flows through that. And then to get from that one on the left to the one on the right, depending on the use case and then also the paradigm, it usually takes between 5 and 15 years to go from just like the really basic model to the actual engine that we see flying in the sky. Yeah. So for this, we're based in these supercomputing centers that have been still advancing at quite at a bit of a rate, at a bit of a cool rate. But as we're seeing like Moore's law come to an end, and just like other issues with supercomputing, with heating and things, we're seeing some of these advances start to hit marginal. They're only marginal advances. Like we're not getting like that much more accurate as to where we were maybe even like 5-10 years ago. So we see quantum computing as being one of the areas that we could maybe take advantage of in the future to really model these systems, because quantum is supposed to offer these pretty powerful computing. I mean, that's why we're all here, right? So initially, I mean, along a similar line to I think what's been said before, we are looking immediately at these NISQ algorithms that are for optimization, and so we care about things like the vehicle routing problem, and then also a similar problem to that composite ply stacking problem, but instead of on the wing, we do it on individual blades itself. And so that's what this graph is. Well, I mean, 2 graphs actually. The plot of different lengths, and we're trying to minimize the amount of the lengths of similar colors that are actually touching one another. And so we can map a diagram such as this on the left to a graph, and then we can color and try to break as few constraints as possible. So we also have some global constraints of just like how many times we can use an individual color and also where we can use those. So that's just kind of one example. And so we've implemented some of the basics of such a coloring instance on the QAOA, and then also some of the extensions, such as the Hamiltonian variational ansatz, which is just that extension of the QAOA. And yeah, so that's been pretty cool. So we've been able to implement a bit of that in the hardware, but most schemes of implementing graph coloring in the hardware requires rather large graphs, and you're requiring, okay, so for instance, doing like a 4-color like this, you would have to have, you're gonna have the whole graph, but then like times 4, and it's a little complicated like that in at least one paradigm of coloring. And so that's kind of, it's somewhat near term, but it's also a bit tricky. Beyond that, though, we also look at simulating diabatic quantum annealing paths. So these are just like the continuous versions of things like the QAOA, such that we can kind of study the dynamics that are going on within something like the QAOA to like fully optimize what's going on, so that we can really observe what's going on in these quantum systems. And then further, though, what we're really using at this moment is just parallel tempering algorithms for this kind of a thing. So we do want to be able to increase the size of these problems that we're able to solve in the future, and also just get better results. And so I think that's kind of why we're trying to use quantum there. Further with variational algorithms, we're looking at the variational quantum linear solver. So it's this result from, I think, 2018 out of Los Alamos. And so this is, again, just treating the quantum computer kind of as a black box, and then we can tune these knobs to give a good output over something that we're optimizing. This is actually a screen, an image from the Zhao-Lukin QAOA paper from 2017 showing the QAOA. But pretty much all variational algorithms take a similar form to this, where we're just plugging in some parameters and then just trying to optimize over those. We're also trying to look at the variational Gibbs sampling methods for lifing in the future and estimating distributions, and that's also something that is going towards. So both of these are also going towards like future quantum implementations that will be a bit more robust, centered more around the quantum singular value transformation. So we do have some clear limitations with current algorithms. I think we're all aware of these. So things like the barren plateau phenomena, and then also propagations of errors through circuits. And so these are kind of nasty issues that kind of really limit what we can do with the current hardware devices. Beyond that, current quantum chemistry is rather limited. Like we don't have the fullest understanding of how to implement those in NISQ devices, and QML itself is kind of it's in some early stages of trying to find the building blocks that then we can eventually build really good quantum neural networks from. Now, this isn't to say that like NISQ is unimportant. These are really cool devices that are showing quantum dynamics and quantum mechanics on levels that we previously couldn't understand. But at the same time, we can't really be confidently applying these to many of our use cases that we have today. But we can still be trying to scale them up in the future. So one thing I really like to wonder is, like, what would we be able to do if we were just given a really good fault-tolerant quantum computer today? And I often think to myself that I would have no idea. It would be like way too cool. I would freak out. I'd try to do Shor's algorithm or something, and then I would break it. But I think that this is kind of a question that we've been pointing ourselves at, trying to figure out where we can go in the future with fault-tolerant devices. So earlier I was talking about computational fluid dynamics as kind of being a central hub of a lot of our business. And so we find that using quantum solvers in the CFD will most likely, I mean, it should, as long as we get to fault-tolerant devices, will give us an advantage with modeling systems using the CFD. And so for this, we're structuring a part of the CFD. So we have this hybrid, we're imagining this hybrid system where only a portion of the CFD calculation is being solved on a quantum computer. And so really this just focuses on solving a system of linear equations. So we're just inverting a matrix. And so for this, there's the two pretty famous algorithms, the HHLD quantum algorithm for linear systems equations, and the QSVT. And so we are currently and actively developing on both of these. And I'm going to walk through both these algorithms, though I'm sure everyone's very aware of how these work. So the HHL algorithm is it's pretty nifty. I think, when did I say it came out? Like 2018? No, it was 2008. The next one's 2018. So in this, we have this kind of costly process of initializing and loading in our state, so that's that B vector. And then the kind of tricky part is that we have to do classically is decomposing the matrix into a linear combination of unitaries. And so this is the part that we have to do ahead of time to figure out how on the machine we're going to really implement the matrix. And then through that, we can run a couple of instances of quantum phase estimation, with then in the middle we have this, this rotation about the eigenvalues, using an auxiliary qubit that if it outputs 1, then we were successful, and then if not, we weren't successful. So it's like the HHL algorithm. It's pretty nifty. It is a bit costly, and that decomposition is a little gnarly. Also, how we actually output the state, we have to iterate through this algorithm a few times if we really want to learn about that state at the end that we actually care about, so solving that system of equations. Alternatively, we could use the quantum singular value transformation. This itself has its own costs, and so in the QSVT, right, we're beginning with block encoding of A, the matrix that we care about, and then we're approximating. So this is a much more general algorithm. So this is like what did Isaac Chuang call it? It's like the grand unification of all quantum algorithms. So it's pretty cool. Oh, there was actually this morning a pretty cool article on the archive about the QSVT, and it's extending it to like distributions, so estimating distributions. But I think a few people already had ideas of that, but it's a pretty cool paper if you guys want to check it out. So this is a pretty general algorithm, and we can do all kinds of things like Hamiltonian simulation, and we can also map it to the quantum phase estimation. We can also do matrix inversion, such that the polynomial that we've kind of got at the top that's decomposed into a bunch of phase factors, when we do it on here, we're just estimating like the inversion of the matrix. So it's this does the inversion directly, and then we can just get B out at the end by applying the inverse of the matrix to the input. So this is another thing that we are working on. So our preliminary results for this, they do track with the classical results. So this graph right here is a comparison of the residual over a bunch of different iterations using either just like the classical solver or either the HHL or the QSVT. There's some notation there about the actual condition number, and then also the epsilon, so the error that we're within for the matrix. And so this is very promising. It's just showing that we are like actually able to do this in a way that is important, and also we will be able to move forward in the future and do this. The tricky part though is that so with the HHL algorithm, we need a lot of unitaries to do like even a simple matrix. So this 65 by 65 mesh, that's I think that's a 4096 matrix, and so to get to that trillion cells, we're gonna have a lot of unitaries that we're breaking the quantum phase estimation into. Alternatively, though, the QSVT is rather costly to calculate the phase values for like matrix inversion for even a 65 by 65 matrix, or a 65 by 65 mesh, while that trillion or even 490 billion mesh is going to take a long while. So along this avenue, we're really focusing on figuring out how we can minimize some of these processes. So we have one effort that's just trying to figure out the best way to break down the quantum phase estimation into this linear combination of unitaries, and so we're really focusing quite a bit on that. We have a couple partnerships within the UK there on that. We further are just looking at different ways of compiling these circuits, especially with fault-tolerant procedures, and how different implementations of error correction might be able to inform one way or another how we actually implement either the HHL or the QSVT within a larger CFD process. But overall, fault-tolerant devices are probably quite a ways away. I mean, unless they're only like 5 years away, which some people are saying. But we do want to be constantly kind of preparing for these, and as we understand the limitations of what we're going to be able to do, and also where we're going to be able to go. So I think this is kind of, these ideas are guiding where we're trying to get to, such that we can improve our CFD models. So beyond this, I think Danny was talking quite a bit about the quantum workforce development, and so at Rolls, we're really trying to push this as well. We have like internal learning programs where individuals or even groups within the company can propose short-term projects, and then they can come learn about quantum and even run some algorithms on hardware and in simulators and emulators. Beyond this, we also have just internships and just quantum openings popping up. Not every day, but every few months. And then beyond this, we also just have a litany of external collaborations towards furthering quantum within the UK, and also just our partnerships all around us so that we can kind of be ready for the future. So yeah, and then also with this, we are funding PhD students, mostly throughout the UK, but just to kind of push the theory of our work. So yeah, I kind of probably blazed through that and overlooked a bunch of things. But yeah, so that's most of what we're doing at the moment. So yeah, we're very optimistic about the future while still being able to play with the quantum devices that we have today. So, yep, thanks.
Questions? Thanks for that. You're talking about some progress in fault-tolerant computing and things, but I wondered, would you like to see more progress in algorithms? That seems a lot harder and slower. What's your thinking on actually that sort of very basic level of improvement?
Yeah, I mean, I think that's like a lot of our focus. So like we have these pretty cool algorithms like the QSVT and the HHL, but it's like realistically when these are implemented on like billion by billion matrices, it's like, yeah, they're gonna be quite complicated. So we have multiple programs that are trying to get these at a level where we could run them if like in 5 or 10 years, we actually have devices that we can run them on. So I think, yeah, we are trying to improve the way that we implement those algorithms. But there is also the idea of like, what about the algorithms, the quantum algorithms that we don't have yet, right? And so I think we're also pushing that with some of the PhDs that we're funding as well. So, thank you.
Thank you for the interesting talk. One question on the increase of granularity in terms of cells you are going to. Do you have an idea of what the impact of that would be? So how much of an improvement do you expect if you can go to higher granularity here?
I mean, this is so with like our current engines is just kind of like absolutely getting to the point where we have like the least amount of emissions possible. But then in the future with hydrogen and then even with electrical, I think that's going to go even farther beyond that. I honestly am not the specialist, so I apologize for the minimal answer. So. But it does give us like when we're getting more fine, it's like always allowing us to like make better and more optimal engines. So that first one that I showed, the like 4.6 billion, it's a pretty optimal engine, and we're able to understand like literally everything that's going on within it, and then verify it through experiments. And so we have. And like the like real experiments that we're like conducting, they're not just on those engines. We also like constantly modify them, and so we have all these test engines that have like slight modifications to make sure that we have a full understanding. So,
thanks.
Yeah, I do have a follow-up question, almost with an open-ended question. Let's call it this way. In an optimization problem or in a graph problem, the more nodes you add, the more time you need to find a solution. I'm wondering with QML, if you add more layers to your neural network, would you expect also that the additional computational workload that results from adding more layers to your neural network, would it be enough to literally wipe down all sorts of advances that you might have found using a quantum approach? I don't know. I'm going here on a limb.
But are you saying classical neural network or quantum neural network?
Yeah.
Oh, so I think
classically, if the more layers you add, obviously you're going to end up hitting, an overhead, right?
Yeah, I think so. I mean, okay, so like could we just use a classical neural network to do these kind of things, like to even model the quantum systems you're saying, or like the other
In a
systems?
quantum neural network, isn't it going to be somehow similar to adding more and more layers? I'm wondering, like, the more layers you add, wouldn't you end up somehow wiping down any sort of improvement you gained from using a quantum approach?
I think that's like an issue. I think like something that we have to be aware of. Yeah, but that's why we like. So like in deep learning, the best algorithms. So like the ChatGPT that we saw last week, and everything from like AlexNet too. All these networks, they're not just like massively all-to-all connected networks. We take advantage of symmetries and also just like patterns in the data to define the networks themselves. And so I think that makes the training itself easier. So within quantum neural networks, then there's a bunch of different kinds. So there's like equivariant quantum neural networks that do have these symmetries, and they try to also avoid barren plateaus with that, while also still remaining quite trainable.
So you still have to massage your data in a sense.
Yeah, I think so. I think that's like, I think it's also like, we can't just throw like quantum or machine learning at all these problems. We have to kind of do it in a tactical way. So that's like, yeah.
Okay, well then, in a related question, obviously, the HHL algorithm, I guess there is an argument to be made that, like, okay, whatever improvements you're gonna get, there is the onboarding and offboarding issue that you just mentioned, and like having to process the data before and after might end up not really making a matrix inversion resolution really that efficient. I'm wondering, what do you think about that?
Yeah, that's why we're, I mean, right now we're looking at both the HHL and then also the QSVT, and I think there's so we're looking at both of those, and then we're also trying to develop right now the kind of like the steps leading into that, so that linear combination of unitaries, so based on the hardware that we're actually implementing it in, and then also just like the compiling steps that kind of go into that beforehand, and those are the places where we're going to really find out if so the matrix that we're caring about is the pressure correction matrix in these CFD runs, and so these are the parts where it's like ahead of time figuring out how we can feed into those, and also in a hybrid workflow. A hybrid workflow might look a lot different than what we have today of just like sending it to a solver. It might we might have like informed solving and like look ahead solving a little bit. So I think I don't know if we can have a verdict today of whether or not it's going to be better, but I do think realistically it should be better, just because I mean we're going to be able to model larger systems ideally. I mean we've proved we should be able to.